Hello, this is Dr. Mears, and today we're going to be learning about natural logarithms. A couple of fun facts, though. Fun fact number one, logarithms have many uses in science. pH is the measure of how acidic or basic a solution is, which also is a logarithmic function. So is the Richter scale for measuring earthquake strength. So there's many different uses. Fun fact number two. Today we will learn about natural logarithms. Natural logarithms are special types of logarithms that are used in solving time and growth problems. Now for an exploratory activity to explain the letter E, let's complete the table. So what we have to do is take each x value and substitute it into our expression here. And I'm going to show you with the calculator how easy that can be done using our parentheses. Now I know this is going to be 1 plus 1 over 1 raised to the first. So I'm just putting the 1 where the x value is. But when I do it in the calculator, I'm going to put parentheses around it. I know you could probably do this in your head, but let's just practice doing it with parentheses. So parentheses 1 plus, open parentheses, 1 divided by 1, close them. So now I've closed this set of parentheses right here. I'm going to then close this set of parentheses. If you ever take a computer science courses, parentheses really matter. All right, now I'm going to raise it. Here's our exponent button to the first power, and I'm going to press enter, and I'm going to get the number 2. So that's what it equals. Okay, let's try it here. 1 plus 1 over, I'm putting 2 in, close my parentheses, squared. So we're going to put that in the calculator, parentheses, 1 plus, open our parentheses for our fraction, 1 divided by 2, close them again so that these match up, so they're always, parentheses are always matching up, open, close, raise it to the second power, and I'm going to get 2.25. All right, let's try it again. To the third power. So now I'm substituting 3 in. 1 plus 1 divided by 3 in parentheses raised to the third power. So now I'm getting these decimals, and our decimals are going to get a little bit longer. So what I'm going to do is I'm going to go to the third decimal place. Now I know in this math course we've been doing 3 significant figures, but I need you to see what's going to happen to this number as we substitute numbers in that are bigger and bigger. So we're going to go to 2.370. So this is a 3 right next to that 0, so it's lower, 4 and lower, so we're just going to keep that as a 0. Okay, let's try number 4. To the fourth, 1 plus 1 divided by 4, closing parentheses, raised to the fourth, I get 2.441. Now, yes, we still have a lot more to do. So you can keep substituting these in, and as you do, what I'm going to do is write down our answers. And I want you to notice, we started when we substituted the 1 in, we started with the number 2. Then, as we kept getting higher and higher x values and substituting them in, this number actually started slowing down. It didn't jump to 3. And actually, all of the decimals expanded out further and further. And look what's happening when we substitute 1,000 in. We see that we get 2.717, and then 10,000, 2.718. And then we jump to 100,000. And if we round it to the third decimal, it still stays as 2.718. So I'm wondering what these numbers, if we graphed this on a graph, I wonder what these numbers and what it would make the graph look like, which is what we're going to do next. Let's explore the graph. So examining the graph of y equals 1 plus 1 over x raised to the x, just for this boundary, I'm just looking from 0 to 5, and our mystery number 2.718. Now, I copied this from online. Thank you for allowing me to copy it online. Notice this is an N and this is an X. It's the same thing. You could just rewrite it if you don't want to confuse yourself. I just kind of picked up on this. You could just rewrite it as 1 plus 1 over x to the x. Either way works. We could have used the letter m if we wanted to, or b. It's the same function. So this is what happens. Here's our x value, here's our y value. Notice we put the number 1 in for x, and where do we end up? We ended up at a 2 for y. And then we put the number 5 in for x, and we ended up at about 2.44, which is what this looks like. And if we kept going and going and going, of course, this stops, I wanted to stop at 5, we're going to get closer and closer to this mystery number. I mean, we went as high as 100,000. This is the mystery number, 2.718. And however, that goes on and on. So that doesn't stop. That's just the rounded value. So what's happening is this curve is going to get as close as possible to the number 2.718. But it's never going to go past it. So that's what I've said with this note down here. As this curve goes to infinity, it will approach Euler's number, known as the letter E, which approximately equals 2.71828182884. I'm not going to go on, but it does go on and on forever and ever. And this actually is going to be introducing you to what's called a limit. And that's what we're going to actually start year 2 with, is talking about limits. As the limit of this graph, it's limited to this number here. It will never approach that. So as we see this x value go all the way to infinity, this is going to keep going to infinity, positive infinity value. It's going to keep going, 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 going. And this is the function that's actually going to keep going and going, 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 going. So this curve right here is going to go to positive infinity. And it's never going to quite get to 2.718. And I'm just going to put dot, dot, dot because it is bigger than 2.718. I just rounded it to 3. But that's what happens with limits. And we've seen that. We've looked at asymptotes, everybody. We looked at curves approaching lines, but they'll never cross them. And that's what a limit is. It's limited to never being able to cross that line, which is a very sad story in math. Okay, so couple things. First, the inverse of y equals e to the x, and that's what we're looking at here, gives us the natural logarithm. So e and the natural log are inverses, just like exponential functions and logarithmic functions are inverses. And you'll see that on your graphing calculator too. If you notice here, we see ln, that's natural log, and above it, you're going to see the little blue e to the x. Sorry, a little fuzzy. Here we have log and 10 to the x. So those are inverses. Remember, this is log base 10, so that's why it's 10 to the x here. So those undo each other. And so that's going to help us to solve problems. All right, so what does this all mean? It's a big concept that you're just getting introduced to. Let's look at some examples that you're going to be held responsible for. The first type of examples are finding exact values of each expression, and we're going to do it to 3 decimal places. So the first one is going to be e to the first. So really, you're going to press the on button. I'm going to clear this out. Now we need e to the first. So we need to get to the blue e to the x button. So we're just going to press second and then natural log. That's how you get to the e. So if you want to write down a little note right here, second, and then the LN button, that gives you this E on the calculator. All right, and notice that it has an exponent here. So we're going to put 1 in. Guess what that is? 2.718. That is this line right here. So this is really E to the first power. That's where this graph is approaching, but never will cross. So we're going to write down 2.718. Okay, let's use our graphing calculator to find E squared. So second natural log to enter. So that gives us 7.3. Now we have 890, so 89. Remember, this 0 is 4 and lower, so that 9 stays. Okay, now e to the negative 1. We have to remember an exponent rule here, because if we try to do natural log, second natural log of negative 1, oh, it works. I was going to make it into a fraction, but you don't need to. That works. So e to the negative 1 is 0.37, and now the number next to the 7 is 8, so I'm just going to round that to 0.368. All right, next, 3e. Notice there is no exponent with the e. And when you put it in your calculator, it's going to want an exponent. So watch, I'm going to put 3 and then second natural log e. Notice it's blinking there. So what happens when we don't have an exponent? What number are we going to put in? Right, we're going to put in the number 1. It wants that exponent. You have to do that. If you didn't, it would give you an error on the calculator. 8.155. This number next to the 4 is an 8, so I'm going to round up. Okay. E divided by 2, so again, we're going to have to put the 1 in. So if you don't see an exponent, put the 1 in. So we're going to do second natural log to the first power. I'm going to move my arrow button over so I'm out of the exponent spot. So be careful, you might have to move that over. Divided by 2. 1.359. The number next to 9 is 1, so I'm just going to keep it as 9. And lastly, again, no exponent for e. I'm going to put my 1 in. So now I'm ready to go. So that's going to be 4e to the first power, moving my arrow over so that I'm not in the exponent spot, minus 5. And I get 5.873. And there you have it, finding exact values using our graphing calculator. That's it. That's all you can do. You can use your graphing calculator. We could have gone to the graph to see what line it would end up, but just use your graphing calculator to find the exact values. Okay, let's look at a couple different other examples, types of examples. The second type that you could have is an actual real world problem. And when I introduced this, I said that our natural logarithms are going to help us solve problems about growth and about time. And that's what we're going to see here. So the growth of a fungus on a tree is modeled by g of t equals 4,500 e to the, this is a 0.3 t, where g, centimeters squared, is area covered by the fungus after t days. Now remember, I like to go back and I like to point out area. So when my problem asks for area, or it gives me area, I know what they're talking about. And I'm going to say time, and then we're going to put days. Okay, so now I know what I'm looking for. Part A, find the initial area covered by the fungus. Now, whenever you see this word, initial or start point or original, what they want you to do is substitute in a time of 0. They want before any days have even passed. What was it when it first started, before any time has gone by? And that means that time is set to 0. That will always be your hint. And so what we're going to do is we're going to substitute 0 in for t. 0.3 times 0. And we're going to put this side into our calculator and see what we get. So 4500, second natural log, e to the 0.3, and we can do times 0. There we go. That's it. Enter. 4500, which makes sense because this would be e to the 0 power, and e to the 0 power is 1, just like anything to the 0 power is 1, and 1 times 4,500 is 4,500. So it's going to be 4,500 centimeters squared. Don't forget your units, it really helps. That's going to be the area. That's the initial area. That's where it started. Initial area. That's when our time is set equal to 0. All right, part B, determine the area of the fungus will cover after 10 days. So what are they giving us? They're giving us T. So remember, sometimes they might give us area. Sometimes they might give us time. They're going to give us one of them. So let's find out. So all we do, again, just substitute our 10 in for T. And we're going to use our graphing calculator, 4500. Natural log of 0.3 times second natural log, of 10, and then enter. And we're going to get after 10 days, it's going to be 90384.9. They didn't tell us to round anywhere, so I'm just going to round to that nearest decimal. So it would be about 90,384.9 centimeters squared after 10 days. Okay, so it helps us to solve problems when we're given time and we have growth. Okay, number 3, simplify the expression. So another type of problem is where we have to simplify. When we simplify, most likely they're going to give you the natural log and the e, Euler's number. These two, remember, are inverses. And what do inverses do? Inverses cross each other out. They undo each other. So we're taking the natural log of e, they undo each other. Our answer is 2. Yes, it's that simple. Just number 2. Let's look at part B. Hopefully you're catching on. We have e, and then we have raised to the natural log of 5. ln and e are inverses. They cross out. We're left with 5. All right, these two down here, a little bit different. Because what we have to remember is, for this one, we have to remember some of our logarithmic rules. Because we have division. And so we're going to have to split this up. We're going to have to split it up to ln, natural log of e to the x. Because we have division, we're going to have to do minus the natural log of e to the y. So it was in the compact version, we have to expand it out. We have to give the e in the numerator a natural log and the e in the denominator a natural log. Then we can cancel out the ln. We're left with x. We can cancel out the ln and the e. We're left with y. And we originally were subtracting. This one, it's in the numerator. We have to remember our exponent rules. And this is why it was really important to go through those last few concepts of exponents and logarithms and understand, because we need to use those rules now. And if you don't remember the rules, take out your worksheets or go back over the videos. So here our exponent rule says this e to the 3 is in the denominator. In order to get it to the numerator, we need to give the exponent a negative. So now we flipped it up to the numerator, but this positive 3 became a negative 3. Now it's in the numerator. We can cross those out. The answer is negative 3. So it helps us to simplify expressions as well. Okay, and the last type of example that we can have is going to be to solve. And this, in word problems, they might actually give you, and this is going to be helpful, when they give you the area and we have to solve for the exponent. And so that's why I didn't do an example here with it, because you have to learn how to solve. So let's learn how to solve. Okay. Part A, we have natural log of x equals 3.4. So what undoes natural log? You're right, e. So what we can do is we can raise this ln x to the e, and we can raise 3.4. We can raise e to the 3.4. So these go in the exponent spots. Both sides get the e. So e raised to the ln x equal e raised to the 3.4. So what crosses out? You're right, the ln and the e. So we're left with x equals e to the 3.4. We know how to do that. We have a calculator. So we're going to do e to the 3.4. And we get 29.96. So x equals 29.96. You could round to 30 if I asked to round to the nearest whole number. All right, part B. Again, we have to solve. We have natural log of x plus 2 equals 1.97. So everybody e gets raised to the natural log of x plus 2. And the 1.97, e gets raised to 1.97. We do that so that we could cross out the e and the ln because they're inverses. I'm left with x plus 2 equals e to the 1.97. And we could do the e to the 1.97. 7.17. So we're going to have x plus 2 equals 7.17. And yes, and now it's just a one step. Let's subtract 2 from both sides, and we get 5.17. Nice. Okay. Part C. Now we have e to the x minus 1. So we were given the natural log, but now we're giving the e. So we do almost the same thing, but we don't raise it. We just give both sides the natural log. That is a weird one. So the e to the x minus 1 gets a natural log, and the 10 gets a natural log. So here these cross out. X minus 1 equals the natural log of 10. Now we just push now we just push the ln, the natural log, and we put 10 in. 2.30 equals x minus 1. And then, yes, we just add 1 to both sides, and we're going to get 3.3. You could put the 0 if you wanted. It depends on what they want you to round to. IB likes 3 significant figures, so that's why I went to 3 significant figures here. Okay, and next, what do we have? We have e, so yes, we're going to be doing natural log. But here's the thing, it's not by itself. See how this e only has the exponent? There's nothing else. There's none of this minus. There's not being multiplied by 2. This, 10's not being subtracted. So what we want to do first is get all of this away from the e. So let's take care of that first. So we're going to use our inverse operations. It's positive. We're going to subtract 10. Negative 2 equals e to the 7x plus 5. 3 minus 10 is negative 7. Okay, after that, this 2 is being multiplied. What do? Undo it using division. So we divide both sides by negative 2. The negative goes with it because we're just dividing. We're not adding or subtracting. So we're at e to the 7x plus 5 equals positive 3.5. Now that we have e by itself, we subtracted 10, divide by negative 2. Now that we have this, we can then put the ln on both sides. This gets a natural log, and this gets a natural log. And so the e and the ln cross out. We're at 7x plus 5. I'm hoping you see a little pattern here. We go to our calculator. We do the natural log ln, 3.5. We get 1.25. And then it's a two-step problem. You're at 7x plus 5 equals 1.25. So you're at just undoing. Subtract 5 from both sides. 7x equals, subtract 5, negative 3.74. Actually, it would be negative 3.75, just because we rounded. 1.25 minus 5 would be negative 3.75 because we rounded, so we can keep negative 3.75. And then divide by both sides by 7. Your standard solving. So we have negative 3.75 divided by 7. We get negative 5.3. Now there's a 5 here, but next to it is a 7, so let's round up. So negative 0.536. And there you have it. Solving using e and natural logs. And because they're inverses, they undo each other. So this has been Dr. Mears' video, natural logarithms, their inverses, simplifying, evaluating, solving, using to solve growth in time problems. Hope it helped.